engineers, supported, guided by ALPA. Last 1 minute to go. Yeah, it is 5:11 and it's time to start.
Let's start.
Yeah, welcome everyone, all attendees, all seniors, all stalwarts. Dr. Rajesh welcomes everyone here on the platform of Igniting Power Engineers. We are here to talk about new topic, lightning protection of MV systems and substations. And today we are very lucky to have very great personality, very renowned personality, Chandima Gomes. Before I give introductions of that great personality, as usual, I start with a few names because without that suppose I can't move. And first of all, I would like to thank Almighty, my family, and now it's time to mention names of my mentors who supported, guided, encouraged, and have been instrumental in my journey of learning, and without which it wouldn't have been possible to reach here where I am right now. And the names start with the very first name, start with respected Honorable PP Bhai Sir, Anjali Chandra Ma'am, Sahil Sir, Pramod Sir, Dr. Kamal Bansal, P. Ramachandran Sir, KK Murthy Sir, Sanjay Agarwal Ji, Apao Sir, Sanjay Patki Sir, PK Patnaik Saab, Dr. Rajamani, Harish Mehta Sir, Manas Kundu Sir, Yugesh Sood, Dr. Vikas, Gopak Kumar, Sanjeev Banerjee, Hitesh Sir, HR Sridhar Sir, Alam Sani Sir. Last but not least, the group of my family, Saket Gupta, Varun, Hitesh, Abhishek, Gulab, and last but not least, Ruchi ma'am. Thank you ma'am. Thanks a lot for giving me technical support. Now I am going to invite the guest Chandima Gomes. And before I invite him, I hand over the stage to that great personality. I would like to tell you about a brief about that great personality. He is the professor of high voltage engineering, the chair ESCOM Power Plant Engineering Institute HVAC, and the director Center of Excellence on the High Voltage Engineering, University of Witwatersrand, South Africa. He is a chartered engineer registered in UK, professional physicist in South Africa, and fellow of the South African Institute of Electrical Engineers. And he was a founder of Center of Electromagnetic and Lightning Protection, Malaysia, and was the first head of the center. He has held full-time adjunct visiting professorship and a lectureship in physics, engineering, meteorology at a university based in Malaysia, Sri Lanka, USA, Australia, Kazakhstan, Pakistan, Zambia, Sweden, Colombia, and Japan. He was a senior advisor to the National Lightning Safety Institution. USA, and a chief advisor to the African Center for Lightning and Electromagnetic based in Uganda, and advisor and mentor to several national lightning research and awareness centers in few countries. And he is a member of Technical Committee 81 of IEC 6205 Protection Against Lightning, and he has contributed a lot in the different profiles. He has conducted over 120 training programs so far in the lightning protection and electrical safety in 12 countries so far. Even this brief about that great personality is not complete. I don't have exact word to say about him. Before wasting further time, I would like to invite Chandima Gomes. Please, Ruchi ma'am, unmute everyone, and there should be a round of applause for that great personality on the Igniting Power Hub. Please unmute.
Okay.
Welcome, sir. Now stage is yours.
Thank you.
And make this stage on fire for next 40 minutes.
Okay, thank you very much. Hope that you can hear me.
Yes, sir. You are perfectly okay. Your voice is okay. Namaste.
And so I hope that you all can see this first slide, which is quite contrasting. It says lighting protection of MV systems and substations.
It is visible.
Yes, and the picture is of a high voltage switchyard. So I deliberately put it in that way so that you can get some feeling of high voltage engineering at the right beginning. So today I'm going into very briefly to talk about the lightning protection of distribution systems, particularly on substations. And this is a rather long presentation, but I have only about, I think about 45 to 50 minutes to complete this. Therefore, what I'm planning to do is to go ahead without rushing into the presentation. So whenever the time is up, I will stop it. So until that time, I'll try to cover whatever we can within this short period of time. And all of you, I'm sure that a clear majority of those who are listening today are from the electrical engineering sector, so that you are very familiar with this electrical transmission and distribution system. And today I'm basically on the distribution transformers and the distribution line, which is feeding the power into that. And I'm not touching the HV side as well as the consumer side or the LV side, which we can cover in another occasion. Now, what are the important points of MV substation protection? Now, when it comes to the lightning protection of MV systems compared to LV systems, we have few differences. One is the high voltage side of an MV substation is more exposed to lightning strikes than LV lines, because the lines are stretched over a very large area, so that the chances of lightning transients coming from the HV side of the substation is much higher than that from the LV side. Now, amplitude of the induced or generated voltages in LV side are more significant than in MV side. Now, this is another important aspect. Although the number of surges that may come from the HV side is larger, the significance of the transients appearing at the substation from LV side is more prominent. Why? The temporal position and polarity of the impulse is more significant in HVME systems than that of impulse in LV systems. Now, for an example, if you take an LV side of a transformer, if a transient comes, you will find that the position of the transient in the waveform is not that significant, because we are talking about less than 1000 volts, most often like 230 or 240 volt RMS line to neutral, so that voltage spike of in the order of 20-30 kilovolts will be quite significant in such case, and it doesn't matter whether it appears at a positive peak or negative peak, or where it is, and the size or the polarity of the signal. On the other hand, when a signal comes from the MV side or the high voltage side of the substation, depending on where in the waveform, the nominal operating voltage waveform, the transient appear, the effect may be totally different. So this is something that you have to be little careful about. Now, when it comes to the HV side of the, when I say HV side, with respect to the LV side, okay, so it is essentially the medium voltage side. When you consider that side of a transformer, the reflection effects become more significant, because there's a long distance that the voltage waveform will travel back and forth. And also, the insulators play a significant role in the MV side compared to the LV side, because in the LV side, we are more interested in the surge protection rather than the insulators when it comes to the transients. Then types of overvoltages. Actually, the most prominent transients with respect to the amplitude are the nuclear impulses, where the amplitude can go up to gigavolts even. But on the other hand, those nuclear transients are very short in time. They are in the nano to picosecond scale. Then comes the lightning impulses and switching impulses. They are in the microsecond scale and millisecond scales. And then in the second scale, we have another very important phenomenon, which we call the temporary overvoltages, which I'm not going to cover in this presentation extensively, but it's a very important point that we have to discuss. Then the system voltage. So today's presentation will be on the transient overvoltages. And then when it comes to the transient overvoltages, depending on the time to peak or front time and the tail time, we have three types: the slow front, fast front, and very fast front. So that depending on the time to peak and the tail time, they are categorized into these three. So that most often the slow front overvoltages comes from the energizing and de-energizing operations of large capacitive and inductive loads. Then the fast fronts are usually from lightning. And very fast fronts come from switching operations of some particular cases like GIS, SF6 circuit breakers, and so on. So keep in mind that here we are concentrating only on lightning and switching impulses, which are not very fast fronts. Actually, we are talking on the cases of a fraction of a microsecond to several milliseconds. So those are what we can take as one block and provide protection measures. And again, I'm not wasting much time on that, just included this for the purpose of completion. We have so many power system anomalies, and the important point that I want to figure out or emphasize in this case is that out of many anomalies we find in the power systems, in the name of lightning protection, we can take only a certain spectrum of transients, which are in the microseconds, fraction of a microsecond up to about few milliseconds. Then again, there are various causes of transients, and one should have some idea about what type of power system operations that will give rise to what type of transient phenomena. And not all operations can give all types of wave fronts. Then we go to the lightning issues in MV systems. Now, issues at transmission distribution line is one point that we are focusing on. Then the other one is issues at transformers and other equipment in the system. So issues at transmission and distribution line, I mean, if a lightning strike a line, say distribution line, what would be the consequences? This is one thing that we are concentrating. Other thing is, if this transient goes into a transformer or substation, what would be the result? Then in a transmission or distribution line, you have to pay attention to one important thing, because in most of the cases where I have done consultancies, people are very adamant on some prejudiced concepts. Say for an example, some people say that, okay, by whatever the cost, you reduce the earth resistance of the tower footing. And some people say that don't worry about the earth resistance of the tower footing or TFR, but we are worried about the backflash over, and so go for lightning protection systems at the tower top. But it's very important to understand that you have to look at the phenomena rather than looking at the solution when it comes to address the lightning related issues of the power lines. Now consider that a lightning get attached to a tower or the shielding wire, and what happen is that a part of the lightning current will flow into the tower very closest to the lightning strike, but another part will go to the other towers as well. Here, just for the clarity, I have taken only 2 towers, but it may go into several towers. Now, if the TFR, the tower footing resistance, is high, then what can you expect? Greater the potential along the tower, higher the TFR, so that more current diverts to other towers. So what you should understand is that if the TFR of a tower is high, then rather than the current flowing into that tower, larger components will go into the neighboring towers. Okay, now imagine that if the TFR is ultra high, now what happens? Apart from a part of the current going to the other towers, the very high potential gradient that will generate along the tower, this may happen, so that there will be flashover across the insulators, and the current passes into the live wires, which are connected in turn into the transformer. So that we call it the back flashover, because the flashover happens from the earth side, the grounded side, to the live or under normal circumstances high voltage side. And this is one major modes of lightning current entering a transformer. Now, if lightning attaches with a phase wire due to the bypassing or an absence of shielding wire, imagine that lightning current strikes straight away into a live wire, either bypassing the shielding wire or in the absence of a shielding wire. What can you expect? There is in one way, there's a chance of the insulation fails in the nearest insulator, and the current will flow into the tower footing. But a sizable current still will go into the transformer as well. Okay, now what is the scenario? Flashover usually occurs at a tower where the TFR is the lowest. Now don't forget that if there is a bypassing of the shielding wire and lightning get attached to a live wire, the flashover across the insulator is most probable usually at a tower where the tower footing resistance is the lowest. So it is understood, isn't it? Because that is the best path for the lightning current to get into the earth. Now, in this case, flashover reduces the overcurrent diverted to the transformer. So if this flashover happens, now it is not back flashover, it is flashover happens, the transformer will be less affected, but on the other hand, the insulator will be degraded. Okay, now let's do a very simple calculation. If a lightning strikes a power line, say a medium voltage line, a distance x away from a tower, and if the lightning has a peak current of 40 kiloamperes, 20 kiloamperes will flow in one direction. This is a very crude approximation. Let's assume that in both towers, the tower footing resistance is nearly equal, so that the current will be distributed among the two towers. Now assume that this is a very hypothetical case where there are only two towers. Now, if the maximum current derivative of the injected current is 40 kiloamperes per microsecond, I am sure that you all know this equation. When you put that, we get something like 30 kilovolts per meter of voltage per meter. Okay, and then if you consider the tower to have a certain impedance, then when the current flows through the tower, there will be another voltage generated. It is not induced. Some people use the word induced voltage in these cases. Actually, it's not induced. Induced means there will be a magnetic coupling. Here it's a resistive coupling, so there is a generated voltage, V2, as you can see there. Now you will find that with respect to a distant ground, the voltage at the point of strike is V1 plus V2. Now, what do you expect when that happens? The voltage at the point of strike may create a flashover between the line and the ground, or line and another line, depending on the the insulation strength of these points and also the V1 plus V2 magnitude. In addition to the faults discussed, face-to-face and face-to-face to earth faults may also be possible. What do you mean by face-to-face to earth? There may be a chance that a flashover happens from a face at the top to a face at the bottom in a multiple line scenario, then from that bottom face to the ground, or if there is a neutral wire, in the case of the lines coming from a star configuration, there may be a flashover to the neutral. Then switchyards, substations, etc. usually have much better earthing arrangements than towers. So I'm sure that you can understand about it. Most often towers, even medium voltage towers, may be placed at locations where the tower footing resistance cannot be taken below a certain value. But usually when you are implementing a transformer or switchyard, then you select a place where you can reduce the earth resistance, so that in these places the earth resistance is much less compared to that of towers. Therefore, in the event of shielding failure or backflashover, the chances of a significant part of lightning current reaching switchyard equipment and transformers is high. So that is why usually we are more concerned about the protection of substations when it comes to the lightning scenarios. Now, prevention of lightning damage. What are the prevention techniques that we use? Shielding wires, surge protection devices, then earthing and bonding. So don't forget that lightning protection is one comprehensive total scenario. You can't address only one part of that. This is something that I always advise to my clients, especially the clients from electrical networks or electrical utilities. People sometimes think that by doing one thing, they can get rid of the lightning damage. But usually it's a whole scenario where you have to address it as a turnkey project rather than giving partial solutions. So what are the things you can do? Correct selection of insulator length. Okay, so before going into the lightning protection, keep your focus on whether the non-transient condition electrical safety measures have been taken correctly. So the correct selection of insulator length, even without lighting, you have to think about it. Then reliability of insulators by selecting appropriate material for a given environment. Now, for an example, if you are having a transmission line or distribution line in a highly polluted area, and if you have ceramic insulators, you've got to be a little careful. For an example, you can have an RTV coating to prevent the degradation of the insulators. The reliability of low frequency fault interruption devices. This is one big problem in many distribution lines, where fault interruption devices, which are installed sometimes about 2-3 decades prior to the present time, and they may not be working properly. Then maintenance of power line corridor. This is another very important thing. The power line corridor, which you can see in this picture on the slide, should be maintained properly. The protection of substation and switchyards from natural disaster and man-made disasters. Now, if I give you one example from your neighboring country, Pakistan, just 4 5 months ago, in Karachi, there were 27 fatalities due to the flooding of the roads, and transformers got flooded. They were submerged in water, and as a result, there were many electrocutions, and also there were mass blackouts happen due to that. So you have to be little careful about these points before you think about lightning protection, because there is no point of adapting lightning protection. Even the best lightning protection in the world will utterly fail if you do not consider about the electrical safety measures that should essentially be taken. This is valid not only for medium voltage protection, but for low voltage system protection as well. Now, I'm sure that most of you know about these things. There are two important parameters when it comes to the lightning protection of MV systems and HV as well. The BIL, the bill, and CFO. Keep in mind that these two are somewhat different, because bill talks about the withstandability, whereas CFO talks more about the failure. Okay, so when you are talking about the insulation parameters, this definition should be understood very clearly. Okay, now I'm going to the protection of distribution lines. So because before coming to the substation, we have to make sure that the as I told you, that the MV lines are much more exposed to the lightning than LV lines, which are mostly in built-up areas or built-in areas. You have to be very careful about how to control or how to manage with the lightning coming into the MV lines, which are leading to the transformer. So this is a very popular equation to calculate the flash collection rate. So in other words, N represents how many flashes that the medium voltage line will collect or attached with per 100 kilometer per year. Then Ng is the ground flash density, H is the height of the uppermost conductor of the pole, and B is the structure width. So that you can see here, the B is from the last insulator, the outermost insulators, or power lines. And then we are talking about the influence of nearby objects. If you have a totally isolated transmission line or distribution line, the collection of lightning to that will be much greater than the case where there are objects in the vicinity. So that the equation Ns equals N1 minus Sf will give you actually the effective collection of flashes when there are tall objects, trees, and so on in the vicinity. This is very important. Let me give you one small example. You know, in the early 2000s, somewhere around 2003, 2004, we found that one of the countries having the highest number of pole mountain transformer failures due to lightning is, what do you think? What country? Out of the countries in the world, the highest number of damage to pole-mounted transformers were observed or recorded in a country you never think that will happen. That is Saudi Arabia. In the southern parts of Saudi Arabia, where the lightning ground flash density is quite small, they recorded the highest pole-mounted transformer failures. Actually, I was one of the consultants for the King Fahd University of Petroleum and Mineral, which studied this matter. Actually, what we found is that although the lightning density in these areas, the landscapes where these transmission lines or distribution lines run is quite small, give me a minute. The damage to these pole-mounted transformers was very high. The reason was that the number of lightning, say for an example, there are only 5 lightnings per square kilometer per year, rather small value. However, as these medium voltage and transmission lines are running in the deserts where there are no other objects in the vicinity, only the line is the only protrusion for a large area, most of the lightning coming to ground terminates at the medium or transmission line of the area. So that is one reason. Apart from that, there was another reason. The ground conductivity of the area was extremely poor. So these two mattered in getting a very high lightning damage to the pole-mounted transformers. And then lightning arrested steel wires, shielding. Now we know that shielding wire is supposed to intersect with the lightning step leader before the streamer from phase wire, so that the shield wires play a big role in the lightning protection. Now, flashover rate from direct flashes on unprotected phase in MV lines. Both corona and imperfect soil effects play relatively minor roles in surge impedance of the phase conductor, leading to a change of about 30%, relatively small. Okay, so that we have done so many studies during the last 10-15 years on the corona and soil effects on medium voltage lines. Unless the distribution line insulation is protected with overhead grounding wire or arrestor, more than 99% of direct lightning flashes will cause distribution line flashovers, regardless of insulation level, conductor spacing or grounding. This is something that we have observed in Malaysia, Indonesia, and some Middle East countries as well. Therefore, to estimate the number of flashovers due to direct lightning flashes, use the equations in the previous slides for a distribution line in open ground or for a partially shielded line by neighboring objects. So it's very important that before you decide what type of or what level of protection should be given to a system, you have to consider the number of flashes that will be collected by the distribution line per 100 kilometers per year. This is the standard parameter. Then overvoltages from lightning flashes to objects near the line. This is another important thing. Observations show that many of the lightning related outages of low insulation lines are due to lightning that attaches to ground or to structures in proximity of the line. I'm sure that many of you know that. Then most voltages induced on distribution line by flashes that terminate near a line are less than about 300 kilovolts. I will show you the equation to calculate that later. So usually these values are less than 300 kilovolts. Don't forget that the transient peak value, okay? The induced voltages tend to have short pulse width compared to the time to half value of a typical stroke. So don't forget that when you're calculating the induced voltage due to a certain lightning current, the induced voltage is proportional to the current derivative, so that the induced voltage must have a duration quite less than that of the current waveform. Yeah, so usually it can be like 1/4 of the duration of the current. They tend to be unipolar, especially for flashes beside the line. Then where an overvoltage level of 300 kV CFO is considered sufficient for lines in an area of high soil resistivity, an insulation level of 420 kV CFO may be more appropriate for areas of low soil resistivity. What is the meaning of this? This is very, very important point that many people forget. If the soil conductivity is less in a given area, the chances of flashover is high. I think I mentioned that in a previous slide as well. Therefore, in a high soil resistivity, if you have a CFO 300 kV, then the low soil conductivity area, it should be like 420 kV. Okay. Okay, now we are going to calculate the maximum induced voltage due to a nearby lightning. I'm not going to the details of that. This is the equation by which we calculate. Usually V is about 1/3 the speed of light. This is the traversing speed of the lightning current in the conductors, so that we will end up with the equation you see below. And now what you are seeing here is the situation in a distribution line. If you have the medium voltage line in a certain area of the certain ground flash density, say high ground flash density for an example, the number of flashes per 100 kilometers per year. Don't forget that ground flash density is something, it is a natural occurrence. It depends on the landscape. Say for an example, in certain part of India, the ground flash density can be something like 12 flashes per square kilometer per year. That is something. Here, flashes per 100 kilometers per year means how many lightning will be attached into the distribution line per 100 kilometers per year. So now you can see that ideal ground is if you consider infinitely conducting ground and do some calculations, then you will find that the CFO increases, or as the CFO decreases, the lightning flashes into the conductor will increase. Okay, and as the ground conductivity decreases, the CFO value for a given CFO value, the flashes per 100 kilometers per year will increase. So that this is the same thing I told in the previous slide. and it is the same thing by another diagram, so I will just skip it as it gives more or less the same consideration. Then underbuilt MV power lines. Distribution lines underbuilt on transmission structures may be especially susceptible to backflashovers. What do you mean by underbuilt MV power lines? You will find that even in India, I have seen in some parts of the country, there are HV lines and then MV lines are built underneath that. So if you have your substation connected to these underbuilt MV power lines, you have to pay little more attention on that, because there are several points. Distribution lines underbuilt on transmission structures may be especially susceptible to backflashovers. Why? The simple reason is that in these areas, when you have a transmission line, it is much taller than a distribution line. So the chances of lightning getting attached to that will be higher. So that the chances of lightning current flowing to the earthing system of these areas, or in these cases, is higher than in normal distribution systems. Now the problem is, if the TFR is high, usually the earthing systems are either directly interconnected or coupled to the soil, so that the total potential of the distribution line or distribution tower will also be increased in the event of lightning strikes, so that the chances of backflashover is higher. Now you will understand that in HV lines, the insulator length will be quite higher compared to, say for an example, if you take a 400 kV HV line, the insulator length is higher, much higher than the case of 33 kV medium voltage line. So the same voltage increment will be seen on HV line and MV line when it is underbuilt, but the backshow possibility is much higher in the medium voltage line. So you have to pay special attention on that. So greater structure heights and larger right of ways will draw more direct flashes to the structures. Then care must be taken to maintain high insulation levels to avoid unnaturally high flashover rates. So you have to be very careful in this regard, because people tend to go for underbuilt medium voltage lines because it's much less costly to maintain such systems, as you do not need a special power line corridor now. You can use the same power line corridor used for the HV line. Then in addition, the voltage stress developed to cause a backflashover is higher on the distribution circuit than on the transmission circuit. Sorry. This occurs because the distribution conductors are further from OHGW. I think I explained these things. Finally, what I want to emphasize is that in this case, you have to pay extra attention on the protection of transformers than in the case of standalone or isolated MV transmission, MV distribution lines. Okay, now a perfect shielding is achieved when lightning strokes possessing peak current greater than the minimum current causing flashover of insulation are intercepted. Now I'm going to another important point, which many people usually do not understand properly, as per my experience in the field. So if I now, before going into the explanation, let me tell it in this way. If I make a statement like this, the chances of a 30 kiloampere amplitude lightning current getting attached to the shielded wire is much higher than a 3 kiloampere amplitude lightning getting connected to the same shielding wire. Do you understand that? Or in other words, lower the peak current of the lightning, greater the chances of that bypassing the shielding wires and connecting or getting attached to a phase wire. How does that happen? Now you see that if there is a 30 kiloampere lightning, the step lead of a 30 kiloampere lightning is coming, and 30 kiloampere peak current is correlated to a large charge density in the lower parts of the lightning channel. What does that mean? It has a greater probability or greater chance of initiating a streamer from the shielding wire than getting one from the phase wire, so that the chances of it getting attached to the streamers developed from the shielding wire is higher. On the other hand, if you consider a step leader corresponding to a 3 kiloampere return stroke current, then this is what will happen. By the time the streamer is formed and directed towards the step leader tip from the shielding wire, the step leader has bypassed that and gone closer to the phase wire, so that the attachment is higher. So that this is another important thing. If you have shielding wires, the chances of a low amplitude current getting attached to the live wire bypassing the shielding wire is higher. Or in other words, the shielding failure happens for low amplitude currents than for high amplitude currents. What does that mean? It means that even though there is a shielding failure, if there is a shielding wire, even though if there is a shielding failure, the backflash over is quite low in probability in a distribution system. So that emphasizes the importance of shielding wires. So therefore, shielding failure may or may not give rise to flashover. Now, as per the IEEE standard 1410, if I consider the sphere of radius, the rolling sphere radius of shielding wire and a live wire in this way, say that it is RS, then you can see that if a step leader with the purple color lightning, if the step leader comes along the sphere which is having a radius RS from the shielding wire, then it will definitely be intercepted with the shielding wire. Okay, hope that you understand that. And if the lightning, just like the yellow color lightning, if it comes from away from these rolling sphere, imaginary spheres, then it will definitely intercept with ground. So in both cases, there is no problem for the live wire. But the problem is if the lightning comes from there, the red color one, because now it is getting into the getting attracted or getting attached into the live wire rather than to ground or to the shielding wire. Now you will understand that when we are designing the direct lightning protection to medium voltage lines with a shielding wire, we have to make sure that the width W which is called the shielding failure width, should be as small as possible. Okay, it should be as small as possible. So I'm not going to the design criteria of this. I'm just giving you the basic idea. Okay, then if the shielding angle is towards the bunch of wires, we call it a negative angle, and if it is away, it is a positive angle. I will just skip this. Then when you are designing a shielding conductor, following basic diagram requirements are part and parcel of a successful shielding arrangement. It may be a transmission line or distribution line, it's the same criteria. The shield wire should always have sufficient mechanical strength so as to bear the tensional forces exerted by the towers and environmental agents. The displacement distance between the shield wire and phase conductors should always be more than the minimum electrical clearance required. Then clearance distance should remain above the minimum safe distance at lowest set points under different environmental temperatures. Now you may be wondering that why I'm talking so much about the shielding wires for distribution lines, because usually shielding wires comes to play in the transmission lines. But keep in mind that in many countries, what we have found is that where the distribution system failure, the system failure due to lightning, in distribution lines, the solution may be, most often may be cost effective when you go for a shielding wire rather than other measures. This may be little contradicting with what you have been thinking all these years, but we have done many calculations and shown that when you go for the very high cost of improving the earthing system, of course you need a good earthing system, but if you have to go for ultra concerns of improving the earthing system and lightning protection surge arresters, perhaps going for a shielding wire to a distribution line may be more cost effective. Then determination of shielding angle of MV systems. Now, when it comes to the distribution lines, a shielding angle of 45 degrees or less is recommended so that most lightning flashes will terminate on the overhead grounded wire rather than on the phase conductor.
Respective sir, please finish in the next 5 minutes.
Okay, sure. And okay, so the time has gone very fast. So that let me come to the determination of protective angle for transmission lines. So this is the equation by which we calculate the protective angle for transmission lines, and I have no time to go into the details, but these equations are available in the standard, so you can adapt them. And again, the shielding angle is computed by this. And then I will go into the lightning surge protectors very briefly. Now, it's very important that when you are selecting a lightning arrestor, now this is another thing that in medium voltage and high voltage systems, the surge protective device or SPD is called the LA or lightning arrestor. Now, when you are selecting a lightning arrestor, it is very important that you should have some idea about the VT characteristics. What are VT characteristics? Whenever you apply an impulse voltage with varying front time across anything, there will be a certain point of breakdown. And this breakdown voltage will be higher if the steepness of the voltage impulse is higher. Okay. And so if you for various impulse wavefronts, if you get the breakdown voltage, you will get a curve like this. And then now say that your load is a transformer, and then you're having a protective device which is a surge arrestor. Now, when you get the VT characteristic of the arrestor and the load, if you see two curves like this, the first one, then your arrestor will protect the transformer because the arrestor will operate before the breakdown happens across the transformer. But if it happens in this way, load has a lower curve than the arrestor, then your your load or the transformer is not protected at all. But if it is like that, the third curve, then up to some extent, the arrestor will protect the load, and after that, the load will protect the arrestor, which is not your intention. And it can also be shown by a statistical method as well. If you plot the curve probability of breakdown versus voltage, then there should be a fair margin between the characteristics of the arrestor and the characteristics of the transformer. So if it is only having a separation like this, your load or the transformer will be protected. And then I'm skipping these risk factor calculations and so on. Then when it comes to types of arresters, there are various types of arresters. These are not only medium voltage arresters, they are both HV and medium voltage arresters. I'm not going to the details of that. Let me just go through these. Yeah. Then surge protection of a typical transformer installation. I think I have to stop from this slide due to the time restriction. Is failure immediate? This is very important for you to understand. No failure due to surge voltages are not immediately detectable. Instead of going into all these lines one by one, let me tell you this. If there is an internal arcing in a transformer, usually it happens between maybe 3-4 turns. So that in a say 500 turn transformer, 3 turns are short circuited due to the arcing. Actually, the transformer will work, but unfortunately there will be local heating that starts happening inside the transformer because of the short circuiting of these windings, and that may cause overheating of the entire fluid and the transformer, and finally it will be failed at a time where there is no lightning at all. So sometimes you may not even speculate or even suspect that it is due to lightning. Then why do transformers fail even when they are protected against lightning? This is another very important question that many people ask. People think that they give protective measures, but unfortunately, if you do not consider the whole scenario comprehensively, for an example, if you have very good surge arresters, but your earthing system is not properly done, or you have improved the earthing system very nicely, but your surge protectors are not good, or you have both surge protectors and earthing system very good, but your connection is done erroneously. Then, especially in medium voltage substations where there is a delta to star connection, it's very important to decide regarding the connection of the earthing systems and so on. And this is a very important point. Then how to minimize, identify failure modes, and then provide required protection. Please keep in mind, I will stop my presentation with this statement. There is no hard and fast formula that I can give in general to protect a substation. Every substation, when it comes to the lightning failure, has its own unique problem, so that you have to analyze each substation separately and give a solution which should be applicable to that transformer. Just like you are getting medicine from a doctor, when you get a medicine from a doctor and if you prescribe it to another patient, just thinking that, okay, I know now because doctor gave me this prescription, you are doing a disaster. Thank you very much.
Sir, thank you very much for this mind-blowing presentation. Okay, and before I go directly to the question answer session, I think I have to invite PP Bhai Sahab. He is available here. Please say a few words and welcome our guest speaker. Please, Bhai Sahab, please come on the stage and say a few words to encourage all the participants and this platform. Hello? Hello?
Yes, sir, you are audible.
I think Bhai Sahab is not here. PP Bhai Sahab. I think he's not getting the voice. Kindly unmute, sir. Okay, I think he's not here. Sir, I'm coming directly to the question answer. Sir, may I start?
Yeah. Rajesh.
Yes,
Good
yes,
evening,
yes,
all of you.
please.
Rajesh, good evening, all of you. Sorry, there was interruption on my
Okay.
side. I'm sorry
Okay.
for that. So I at the outset must congratulate you for organizing this wonderful session on lightning protection of MV system, because this is a subject probably we have heard very little on this subject. This is a very
Yeah.
unique subject. You could pick up, and I think we do have we had the lesser experience in our professional careers, but I say with your ingenuity, with your probing the things nicely on your side, you selected a very good topic. And simultaneously, Mr. Chandima Gomes, he has done a wonderful justification on the subject. And see, when he talks about shield wire, when he talks about the surge arresters, when he talks about the earthing, and he has quoted the practical instances also. It's the damage of the distribution transformers during his lecture. So it is really an eye opener for all of us, and he's done a wonderful job. And again, I say this is an area, distribution sector remains neglected on our side. Mr. Gomes, particularly in India, we are of course focused on generation transmission, but distribution sector exactly, you see, we still have to go a long way. And your contribution in this presentation has been wonderful. I think we all are enlightened, all our participants there are going to be enlightened, and take care of what they can they can take precautions while working on in their organizations. A wonderful job, and I again congratulate Rajesh. He is doing a wonderful job since he created this portal, see, for all the engineers, see, igniting power engineers. But it's really a wonderful job he is doing, and this is the 5th session he has picked up and organized for us. We really are really
Thank you.
congratulate him, all of
Thank you, sir.
us. Thank you so much, Rajesh, doing a
Thank you.
wonderful job, and kindly go ahead in the same way. All our
Thank
best
you.
wishes.
Thank you very
Thank
much.
you so much. Thank you so much. Wonderful
Sir,
job.
I'm
Thank you.
going to the question answers. The very first question I have noticed from all the participants, they want you to answer, sir, is if you says the IS or IEC 62305 is not applicable, then what IS, IEEE or IC they should refer to understand that subject in a better way? Very first question, sir.
Okay, this is a very important question
Hmm.
as well. Now, what you have to understand is that unlike in the case of low voltage protection, which is comprehensively covered by
Yeah.
IEC 2305 1 to
Yeah.
4, and the standards will be updated very soon in 21 and 22. And also, if we go to the uh, the American standards or New Zealand, Australia standards, all these have one block, N block for low voltage protection. But in contrary, when we come to medium voltage and high voltage protection, we don't have such one set of standards to refer. Now, say for an example, if you take the earthing of substations, then IEEE 41C uh, comes into play, and there are several IEEE standards. I'm sure that you have heard of the IEEE Green Book.
Yeah, yeah.
Uh,
142,
I-
142. IEEE 142.
yes, an IEEE Emerald Book.
Yeah,
These
ML.
are these are basically addressing the substation earthing. Then when it comes to the lightning protection of the surge arresters of MV systems, we have another standard. So what I can tell you is that rather than now reading out all the standards at this moment, if you can email me, my email is very simple, chandima.gomes@gmail.com. I will
Okay.
send you a comprehensive list of all the standards that you have to look at uh, depending on what aspect of MVO HV protection systems you want to address.
Thank you, sir. Thank you very much. Coming to my next question. In your presentation, you talked many times about the tower footing resistance. But I feel instead of resistance, we should emphasize on the impedance because for lightning, the impedance play a very vital role.
Okay, this is a question where we are struggling, or we are having a dilemma between the theory and practice, because you're very correct when it comes to a transient phenomena or very fast time varying phenomena. Rather than resistance, the inductance, especially inductance and capacitance as well, play leading roles, especially when you are calculating the voltage generated due to a current flow. LDI by dt dominates the voltage induced or voltage developed. However, if you look at all standards, except for something like the DoD, Department of Defense standards in USA for EMI, EMC concerns, everybody gives the limiting resistance value. The simple reason is, if now imagine that if I say you should have a 8 ohm impedance for the tower footing resistance at 20 kilohertz frequency. Or I will give you a Fourier spectrum at which your impedance should be less than this value. Now, how many engineers could be able to take this measurement? So, because of that problem, as we do not have very convenient or straightforward ways of measuring the impedance under transient conditions. Now, for an example, if you want to measure the time varying impedance at 8 by 20 microsecond current waveform, you have to take a 8 by 20 microsecond current waveform generator, which is quite bulky, into the earthing site. And then together with that, you need oscilloscopes and various probes to do the measurement, which is almost impracticable in many parts of the world. This is why we do not prescribe the impedance, although, as you very correctly figured out, it is exactly what we have to specify. But unfortunately, we can't do that. But as a remedy to that, what we do always is, while specifying a resistance value, we always give some specifications for the earthing configuration. Now, if you look at 623.053, you will find that there are type A earthing system and type B earthing system, and we give some comprehensive ideas of how to develop a distributed earthing system by which the impedance will be reduced.
Okay, sir. Okay. But if you talk about, if I start talking about the Indian market, in Indian market, many manufacturers have come out with impedance earth resistance, tower earth resistance measurement method. What your view on that?
I think that I'm really doubtful about the accuracy, or at least what they are really talking about, because I have gone through some documentation sent to me by a few of my Indian colleagues. What I find is that these so-called instruments have not much meaning. I mean, say for an example, you can develop a impedance measuring instrument which measure the impedance at a very low voltage level, but at 5000 hertz or 5 kilohertz. But that does not represent the impedance which really will be effective in the event of a lightning current flowing in the earthing system.
Okay.
Because if you get the Fourier spectrum of lightning current, it is quite different to a single frequency that you are giving at a very low voltage.
Agreed, sir. Agreed. Very, very good insights. Thank you very much for that. Coming to the next question, you mentioned about there is chances that the shield wire may fail and the lightning may directly strike to your phase conductor. But what is the probability of striking that lightning direct to my phase conductor? Because we are taking full precautions, shielding angles is there. We are making so many calculations. We are getting our design approved. Is it possible to have that failure?
Yes, because we have seen many parts of the world in many instances that shielding wires which are designed exactly according to the standards have been bypassed. As I told you, the shielding failure usually happens with low amplitude lightning.
Right.
And when you beg your pardon?
Yeah, you are right. I have noted that thing.
Yeah. So now the thing is that the electrogeometric model, which is included in the in both IEC and IEEE standards, are designed in such a way that you are considering a certain level of protection. That means we consider that my shielding wire efficiency is calculated if the lightning current comes above a certain value. Okay. Now, say for an example, most often, if you go to level 3 protection, we assume that the lightning current will have, say, level 4 protection. It has an amplitude 16 kiloampere or above. If it is the case, then my shielding wire will interact or intercept with the lightning. So that depending on the level of protection that you are considering, we consider that there is a certain threshold minimum current which will be intercepted by the shielding wire. So that is also, don't forget that is a probabilistic calculation. We can't say exactly if the lightning current is above 3.5 kiloamperes, definitely the shielding wire will interact, and if it is less than that, it will not interact. But there is a probabilistic determination that we have to make. And what we are doing in engineering is that we take a certain calculated risk. Because if we go beyond, say for an example, if I am going to 99.999% success rate or 0.0001 failure rate, then the cost of my protection system will be very high. And as I told you, when you go to a certain level of protection, we make sure that even if there is a bypass, that will be a lightning with small current, so that the bypass will not cause a shielding failure. So not shielding failure, I'm sorry, a back flashover or flashover.
Right, sir. Right. Thank you, sir. Thank you. I am coming to the last question from my side, then I will call some participants who have some queries. What is your view on the VFTO studies for the GIS systems we are providing in our system? Very fast transient overvoltage study. And as per the IC, that is not applicable up to 66 kV system. It is applicable when your system level is more than 66 kV level. What is your view on that? Should we go for that, or you should?
Yes, I think GIS systems are the future of medium voltage and the substation systems in the future, because in the world now there are so many studies going on in this case, and it has a very good future. And I think, if you ask my view, several of my students are now working in this area. So unless there is a revolutionary system comes in the next 2-3 years, that will that will be the future. That's what I can tell.
Now I would like to invite Ravi Kumar. He has some question related to TFR and the use of double insulation. Please unmute yourself, Raviji, and ask the question directly.
Sir, good evening. Sir, my first question is regarding you're talking about tower footing resistance, but in IEEE for calculation of arithmetic calculations, there is nothing discussed about tower footing resistance of the transmission line. What will be the, if tower footing resistance is on a higher end of a transmission line, what will be the implications on the substation? That is my first question. And second question, sir, for substation, when we need to go for double tension or double suspension insulator for to avoid these arc flashouts. Thank you, sir.
Okay, so your first question is there is a very straightforward answer. When it comes to the TFR, it plays a very important role which you have to understand correctly. It is not just like you reduce the TFR as much as possible and your problems will be solved. It's not like that. Now you see, if we have a tower with very high TFR, and imagine that the shielding wire or even the tower itself is attached with a lightning. And when this lightning current flows into the earth through this tower, if the TFR is high, say that it has a very high value. Now what happens? There will be a very large potential gradient developing along the tower. So the result will be a sizable voltage will appear across the insulator. Okay, so that there is a very high chance of a backflash over, and then the transient will go along the face wire to the transformer or to the substation. So this is the problem you have when you have a very high TFR. I think the IEC standard is addressing this better than that. I can't remember the name, the number of the standard. but I can let you know if you send me an email. But on the other hand, consider that you consider only one tower and reduce its earth resistance as much as possible. Okay, so now what happened is that, so other towers in the vicinity are having high TFR, only one tower having very low earth resistance. Now, if there is a lightning current bypassing the shielding wire and connected to a live wire, then there is a fat chance that always there will be a flashover. Now, not back flashover, flashover from line to that tower, which is having a very low TFR, so that the insulators connected to this tower will be degraded very fast. So these are the concerns that you have to be little careful about. So what we advise is that if say that you have a certain segment of a distribution or transmission line where at one tower, say for an example, this tower is close to a paddy field where the resistance, the TFR is very low, then what we say is that at that point, you better have a surge protective device in parallel with your insulators, so that the lightning current will flow through the surge protector and get earthed. And in the same manner, if you have a tower which is in a certain pathological site where the TFR is ultra high, extremely high, and there is no way that you can reduce the earth resistance. So in such cases, what we advise is, now here the problem is, in the event of a lightning getting attached to that, unfortunately, these type of towers are usually at very high elevations, because in mountain tops, you usually know that there are rock which will prevent you from getting a very low earth resistance or even appreciably low earth resistance. So that in these cases, when the lightning strike, there is a very high possibility of backflashover, and the current goes to the transformer through the live wire. So in such cases, what we advise is that you increase the size of your insulator more than what is required for a given voltage level. So by that, you can greatly reduce the damage to the transformer. So this is why I said that this is an area where, unlike in the LV protection scenarios, you need some unique solutions, taking case by case, rather than giving one general protection scenario. Okay.
Thank you very much, sir. Thank you very much. Sir, I have seen one thing when we talk about the DSLP calculation for substation for EHV system or medium voltage system. We have only one tool available, that is the chapter number 31 of book Reswick book of lightning protection, chapter number 31. Every party, every vendor is giving calculation based on that chapter only. We don't have any other method to calculate DSLP calculation for substation protection.
No, there are actually, just send me an email. I will send you.
Okay.
I can't send you the book, but I can send you some references.
Okay. The last question, I would like to know, Dr. Vikas Almani, sir, please come and ask your question and say vote of thank also.
Yes, Dr. Gomez, very, very nice presentation, actually. and very enlightening actually. It's light on lightning actually. That was that was great thing that you've done. And I think that this is one of the responsibility of all of us basically to educate or create awareness of this particular subject. Thanks for coming in today, and this was really a excellent marvelous session. So I also have few questions for you actually. So it is for all. You mentioned for the underbuilt structures that only one arrestor at a line is sufficient, that is what you mentioned, if I understood it correctly. What about other lines? Was it, you mentioned that, just one arrestor in a phase is okay or is sufficient.
Uh,
I couldn't get this
what I
very clearly there.
okay. No, what I said is the main point I was trying to emphasize is that when there are underbuilt medium voltage lines, you have to give more concern about lightning protection than isolated systems, because this is in contrast to the common belief. Because when you have underbuilt medium voltage lines, the common thinking is that, okay, now you are lightning protected because there are taller towers. But the issue is this: when you are underneath a tall towers or tall structures, then the lightning getting attached to these structures is higher. So that unlike you're having isolated medium voltage lines, when you have underbuilt lines, the area getting intercepted with lightning is higher. So whenever there is a lightning current injected into a transmission line, the earth potential will rise.
Okay.
And most often these medium voltage lines have the same earthing system shared, or even if it is not, they are coupled to the soil, so that the entire medium voltage line will also increase in the voltage. But the problem is, in the case of the transmission lines, you have much higher insulators, larger insulators, so that backflash over probability is less. But the same voltage which is exposed by the medium voltage line has much smaller insulators, so that backflash over is greater. So what I try to emphasize is that in medium voltage lines underbuilt, you should pay special attention to the surge protection.
Exactly.
Not that one surge protector is enough. You
So
have to give
I
more
misunderstood from the text, maybe.
more emphasis
Okay.
to the.
Yeah. The second question that I would like to have from you is it's about the distribution side, about the LV side. When we have a lightning strike on the MV side, for example, and it tries to travel everywhere in the ground through the lines from one tower to other, and finally basically reaches the transformer. Other side it's reaching towards the substation. Actually, it's a kind of transverse. So when it reaches the transformer, actually, there is a capacitance between primary and secondary of the transformer that also comes into the play actually, and this capacitance in microfarads or picofarads basically that plays a role for this high frequency thing which is coming in. So can you just say a few lines about this, how that helps lightning to transfer from one side to other, or it doesn't play any role?
Okay, so actually today I did only half, I think less than half of my presentation. That's why certain part
Yes, I
regarding
understand that,
actually
but we invite you
substation
again
is,
for that.
yeah, actually I didn't touch the substation protection. It was up to the substation protection I did so far. Now the thing is this: whenever you have a transient coming from the medium voltage or high voltage side of the substation, and imagine that it gets bypassed through the surge protector in the medium voltage side, you think that everything is okay. No, nothing will be gone into the low voltage side. So there is a certain point that we forget in this case. Now I'm talking about the the surge protectors in the medium voltage side. Okay, so
Yeah.
say that the total voltage is filtered into the ground. But now the problem is you are having a delta to star configuration where the star neutral is connected to ground. So that here we are coming to a very important point that unfortunately no standard specifically giving a general idea about how much you have to separate the body plus surge protector earth and the star neutral earth. Some people say it is 4 meters, 8 meters, 20 meters. Australian New Zealand standards say 20 meters. And some people have company standards saying 4 meters and so on. But the problem is that depending on the soil resistivity, the effective length to decouple the two earthing system will vary. So now we are thinking about giving some other solutions like having a potential barrier in between, like titanium oxide. But so the problem is whatever the system you have, there is a chance that you're getting coupling through the soil of this transient to the low voltage side, and then it will appear at the subscribers or the
edge, the
users
side. The
place.
user side.
Yes,
Exactly.
yeah. And if so this is one problem, and sometimes people without knowing about it, they integrate the two earthing systems, and which will cause enormous problem for the power system subscribers. So the other problem is if there are no SPDs, then when the lightning transient is flowing in the primary, a sizable transient voltage will be transferred into the secondary side, both by magnetic coupling and capacitive coupling. So
Exactly.
that this will appear at the user's end, which causes very big problems, because we have done some prototyping of this effect and found that sometimes 70 to 80% of the lightning energy in the primary can be transferred to the secondary.
And what
So
about
it's
reverse? What about reverse? Suppose there's a tower from the on the side of the customer or the end user, and there is a strike on the tower, which is not a MV tower. Let's say it's a telecom tower, and then lightning comes into ground and tries to flow via secondary towards primary, actually from the reverse direction. Does it amplify?
Yes.
What? Maybe good to know for all.
Actually, in that's a special case that we have to discuss. At least we need an hour to talk about that, because it's a big problem in many countries.
Sir, taking the importance of that note, I would request you once again kindly spare one more hour anytime of your convenient and give that 1 hour to our platform to come again and enlighten us with your thought, with your experience. We request on behalf of
Thomas, it will be required actually. Basically, it's good for all of us, all the fraternity here. It was a very nice session today, and a lot of discussions are there. Maybe next session we will have more of discussions and lots of presentation. We have a lot to ask from you. Great.
Now, for that, I will be requesting you again, and I will be in your touch. And accordingly, we will set one other day of your convenient. And accordingly, I will set up one ad for that so that more people can join this time to get benefit of your experience you have. With that note, I would like to say thank you very much, sir. Thank you very much for accepting my invitation. Thank you, sir. Thank you. Namaste.
Thank you. Thanks, everyone. Thank you.
Namaste.
Thank you.
Namaste, sir. Thank you, sir.
You're welcome. Take care.
Thank you. Thank you once again, sir. Thank you everyone for joining me. Thank you once again. Namaskar to everyone.